In this video, we're going to look at regulation of the citric acid cycle. So the citric acid cycle, to keep it running, the cell can do a few things to modulate the flux. And these things are the availability of the substrates, the cell's need for different intermediates, demand for ATP. All these will go into how fast the citric acid cycle is running. And just to show you the amount of energy we've gotten so far through all our talk of metabolism, we recently ended with the citric acid cycle where we get 3 NADHs, an FADH2, and a GTP. Well, remember from glucose, we get NADHs as well, we get some ATP. All these NADHs will go to oxidative phosphorylation, and that will give us ATP. One NADH is roughly 2.5 ATP, so that's where we're getting the number 5 here. And remember, from glucose, we get 2 pyruvates. So for each molecule of glucose, we get to run the citric acid cycle twice. That's why everything is doubled here. And so from one glucose molecule, we get 7, 12, 27, 30, 32 ATPs from one molecule of glucose. So the citric acid cycle produces a lot of energy, but if we don't need energy at the time, we don't want the citric acid cycle to run. And so the place that we really want to regulate the citric acid cycle to begin with is at the very beginning of the cycle. That is the entry of acetyl units into the citric acid cycle. Now, we talked about how we can take pyruvate and using 3 enzymes, E1, E2, and E3, we can make that into acetyl-CoA. That process is irreversible, and we don't really use acetyl-CoA for anything else inside the body. So once we have acetyl-CoA, we're going to be running the citric acid cycle. So we want to make sure we regulate this system, that we aren't making energy when we don't need it. And there are 2 systems that we use to regulate this complex. First is product inhibition. NADH and acetyl-CoA will compete for binding where NAD plus and coenzyme A bind. So they will try to outcompete our reactants, our products will. And when they bind, they actually drive the reaction backwards. E2 and E3 will run backwards now, and we'll get NAD plus and coenzyme A from that. So just by inhibiting our enzymes with our products, we're stopping it, and in some cases we can actually make it run in reverse. We also can use covalent modification by phosphorylation of E1 to inhibit this first step of the citric acid cycle. So NADH and acetyl-CoA will activate the enzyme pyruvate dehydrogenase kinase. And what this will do is that it will phosphorylate a serine residue on pyruvate dehydrogenase. Once E1 has been phosphorylated, this complex is now inactive. However, it is actually possible to reverse this. If you have insulin, insulin will turn on pyruvate dehydrogenase kinase, which will, pyruvate dehydrogenase phosphatase, over here. That's what insulin turns on, and that will dephosphorylate our enzyme and have it start working again. Again, kind of makes sense. Insulin saying we have glucose available, so if we have glucose available, let's start making some energy through the citric acid cycle. Pyruvate, ADP, and calcium can also inhibit the process of pyruvate decarboxylase as well. So that's the very beginning point. Now let's look at the actual enzymes inside the citric acid cycle and see which ones are ripe for inhibition. So we talked about this in glycolysis and gluconeogenesis. The enzymes that are far away from equilibrium, that is the super negative enzymes, those are the ones that are targeted for regulation. Those are the ones driving this whole process forward. If you look at delta Gs for these enzymes under cellular conditions, which is this delta G that I'm circling right here, you have 3 enzymes that are far from equilibrium: citrate synthase, isocitrate dehydrogenase, and alpha-ketoglutarate dehydrogenase. These are going to be our 3 enzymes that we want to inhibit that will stop the whole cycle. And flux is really controlled by three mechanisms: how much substrate is available, inhibiting the enzyme with its own products, and feedback inhibition from intermediates further down in the cycle. And our big regulators here are going to be acetyl-CoA, oxaloacetate, and NADH. And here on this graph, I'm going to show this graph for a couple slides now. Where the red is showing, that's showing you inhibition. For example, NADH is coming here and it's blocking this enzyme, this enzyme, this enzyme, and this enzyme. Acetyl-CoA is blocking its own making, so on and so forth. Green means turning on. So green is speeding up that enzyme. Red is slowing down that enzyme. So let's take a look at how oxaloacetate and NADH function to help control flux through the citric acid cycle. So oxaloacetate is in equilibrium with malate, the concentrations up there too. And we can talk about this concentration with this constant K. The concentration of oxaloacetate multiplied by the concentration of NADH divided by the concentration of malate multiplied by the concentration of NAD+. This ratio must always be held in the body. It's an equilibrium ratio. So let's say that your muscles are working and you're doing a lot of respiration. Well, your NADH will decrease as you do oxidative phosphorylation. As your NADH decreases, the numerator decreases. And remember, we want this ratio to stay a set number. So what will happen is that malate and NAD plus will be converted to oxaloacetate and NADH. Therefore, we will increase the amount of oxaloacetate we have. And when we increase the amount of oxaloacetate, we're speeding up the cycle. We're throwing more substrate into our cycle, which means we're going to generate more ATP. So that's how oxaloacetate, and just an example of NADH, can control the flux of the citric acid cycle. Succinyl-CoA is an example of competitive feedback. Succinyl-CoA will go and inhibit the enzyme that actually makes it. So that's direct feedback. It can also inhibit other molecules further out. And what all these inhibition schemes are doing, they're really helping all the concentration of your intermediates stay within reasonable bounds. As you can see, most of these reactions are near equilibrium. So if you get too many intermediates, it will start running backwards at some point. So you really want all these intermediates, the concentrations of these, not to fluctuate too much, so your citric acid cycle can continue to run smoothly. Now some more regulators here. So ADP is an allosteric activator of isocitrate dehydrogenase, while ATP will inhibit that. Again, should make sense. ADP means we have lost energy, please make some. ATP says we have a lot of energy, don't make any more. Calcium, we've talked about calcium quite a bit in Biochemistry 1 and 2. Remember, calcium is what you need to move your muscles. Well, here, calcium also, at many points, speeds up the citric acid cycle, which again makes sense. You release calcium when you want to move your muscles. So if you're moving your muscles, you're burning ATP. If you're burning ATP, you need to make more ATP. So turn on the citric acid cycle when you move your muscles. So all of these citric acid cycle enzymes are thought to reside, or a lot of them at least, in a metabolome. We already talked about metabolome a little bit, but a metabolome is organized in enzymes of a pathway. So the enzymes catalyzing sequential steps will interact and channel intermediates between each other. We talked about this with pyruvate dehydrogenase E1, E2, and E3. This allows your reactive intermediates, I should say protection, not production. So reactive intermediates aren't going to have any side reactions. Your local concentration of intermediates will increase, which will speed up your catalysis. And this was hard to find out experimentally, that citric acid cycle enzymes were in this metabolome. because they're not held together very strongly. Unlike pyruvate dehydrogenases, these are held very strongly. Citric acid cycle, we think, are held together by very weak forces. So when you try to find them out experimentally, they would always dissociate from each other. But there is rising evidence now that the citric acid cycle enzymes are actually in one giant complex. Don't know what it looks like because it's weakly held together, but there is evidence that that is happening. And we think that this complex is associated with the matrix side of the inner mitochondrial membrane. And that is actually where succinate dehydrogenase is anchored. So it would make sense that all your other enzymes are around this enzyme that is permanently in the membrane. And with that, that's the end of this video. I will see you in the next video.